All right, AP Calc students, you are probably so fed up with doing these stupid volume questions, and maybe even the area part is tripping you up. So I'm going to walk through one of them, and we'll start with the area portion, start with just a little bit of algebra, and then we will get into some of the volume. And hopefully we can clear something up for you. If not, hey, this was free, so take what you can get. But you know, if I can make your life a little better with these volume questions, you know, when you find the region between a set of curves, find the area of that region, and then, you know, based on like a rotation, for example, find the overall volume, then I'm happy. So let's take a look. Let me share my screen. Let's see what's going on. All right, so the question says, let region R be the area in the first quadrant bounded by these curves. Okay, so first quadrant, that means both X and Y will be positive. Okay, so 6 minus X, Y equals 6 minus X. Let's take a look at that one. It's always good to draw a little sketch, even if you're not asked to, so that you know kind of what you're talking about here. Okay, so 6 minus X, that's going to have a y-intercept of 6, actually an x-intercept of 6. Okay, that's kind of what's cool about this structure. It's a line that has a slope of -1. All right, if you want some review with that algebra, you can, you know, find videos on slope-intercept form and all that. We're going to try to do this one without a calculator. So, you know, if you are allowed to use a calculator for this question, which you very well may not be able to, you could just graph it, though, on a calculator anyway. So we're going to go from this point to this point. And that's going to be y equals 6 minus x. All right, what else do we have here? Y equals the square root of x. What does that look like? Well, hopefully you're somewhat familiar. That graph kind of goes up like a, you know, like you're, I don't know, throwing a something. And it zooms through the sky like you're throwing a dart, maybe. It goes like that. So here we are. We're going to go from the origin to the spot. And hey, we have an intersection point. We don't know where that is yet. Maybe you do. Maybe you're that smart. But we're not quite there yet. So this is y equals, let's see, square root of x. What else do we have? Oh, the y-axis. What is that? That's this guy. Hopefully we all know that. I'll shade it in blue for emphasis. Okay, so there we have it, folks. There is our region. Purple, red, blue, pink, I think, actually. Anyway, we're going to shade it in green. Why? Because that's what we're talking about. That is this. We don't know a few things. Well, let me label it. We'll call the region R. We don't know a few things, okay? We don't know how tall it goes. Again, maybe you do. We don't know where that intersection point of purple and pink is. That's very important. We do know that the boundary to the left is the y-axis, okay? That would mean where x equals 0 is one of the boundaries. So what do? A, sketch the region, part A asks for that. Sketch the region bounded by the curves and determine the points of intersection between the two functions, okay? So the two functions, they're talking about these y equals. Those are functions. Whenever you have something in y equals, review from algebra, that means that it is specifically a function. Sometimes with these problems, you're working with non-functions, meaning you might have an x equals, and you might have a y squared in there. And flashback, vertical line test. If a curve does not pass the vertical line test, it's not a function. That's okay. We have the tools now to be able to find areas for those. Okay, so again, let's use algebra / some smart reasoning to find what is that purple-pink intersection point. So I would suggest if you're, you know, one solid method is trial and error. Try some basic points, okay? Well, let's plug in 0. 0 for x. 6 minus 0 is 6, and 0 is 0. Those do not intersect, right? Remember, the goal is to set those two functions equal to each other, and this point right here is going to be the point where the function values are equal. So what if we plug in 1? Well, we're going to get, we would get 5 on the top here, and we would get 1 on the bottom. So that's not going to work. Let's try 2, okay? 6, write some of these down too. And there is a non-trial and error way to do this. Obviously, using your calculator, you can find the 2 intersection points of the graph. But there's an algebraic way we can do this too. I'll show you that in a second. Square root of 2. Nope, that is not 4. Okay, so it's not that one. Let's try 3. 6 minus 3 is 3. Square root of 3. Nope, that is not 3. So not that one. Let's try 4. 6 minus 4 equals 2. And the square root of 4, hey, it's 2. Okay, so again, if you are on the weaker side of your algebra skills, especially because when I'm recording this, this is mid-April, and the exam's coming up, sometimes you can just try these out and see, oh, that's the intersection point that I want to work with. Okay, but the other thing is you can use your algebra skills. Again, we talked about, we want those function values to be equal to each other, so let's actually just set them equal to each other. That means we're going to say 6 minus x equals square root of x. And now what we can do, and this does have some things you got to be careful about. We'll talk about that in a bit, but let's square both sides. No, I don't like green. That's too bright. Let's square both sides. I'll just keep using black. Square, square. And the warning signs have to do with, later on, we're going to have to check some positive, negative business going on. But we don't need to worry about that quite yet. So 6 minus x squared. That is not 6 squared minus x squared. Again, it's very important in calculus that you remember your algebra. Please, please don't try to do that. Okay, 6, remember, use your FOIL. That's 6 minus x times 6 minus x. So that's going to give you 36 minus 12x. And that's going to turn into a plus. X squared equals x. Okay, that will help you find the x value in which these are equal to each other. Now set it equal to 0 minus x minus x. That's going to get 0 over here. And I want this in standard form. So let's move these around. Where did the negative 13x come from? Negative 12x minus x becomes negative 13x. Okay, factor. What 2 numbers multiply to give you 36 and add to give you negative 13? Oh, negative 9, negative 4. So again, some of this is a blast from the past for you. If you're a little lacking on your algebra skills, that's why I talked about trial and error there. Graphing is the easiest way to do this. If you have a calculator with you, graph this and figure out where the region intersect, where they intersect each other. 4, right? We can plug 4 in, just like we talked about here. Well, wait a second. Can't I do x equals 9? X equals 9 question mark? Okay, let's talk about why that will not work. If you go back to your original functions, we plug in, let's look at the second one. We plug in y equals the square root of 9. Okay, you are going to get the point 9 comma 3, which by the way is going to be like over here. Those do not intersect over here, right? What if we plug it in up top, the top function? 6 minus 9 is negative 3. Interesting. 3, negative 3, 3, negative 3. Why did that happen? That happens because when we square in the beginning, the danger that you have to be careful of is now it's almost like you're ignoring the sign, because when you square something that's negative, you'll get the same positive answer as if you square something that's positive. And that's why, yes, they have the same absolute values, but no, they do not have the same actual value. Okay, so 9 does not work. Okay, x, it is not an intersection point. So 4 is the one we care about, and we also care about the y-axis. So we don't really need to worry about that coordinate yet and that coordinate yet, but we do know them. It's 0, 0, and that's going to be a y-intercept of 6 because that's where it crosses y-axis. So that is going to be 0, 6. It's always a good idea in your sketch to label all the points that are intersection points, so you know what you're working with. And then this one we said was 4, and then plug it into either function should be the same thing. Yes, it is 2. Okay, that's what we have to work with. Very clear. Good. Sketch 3 and determine the points of intersection. Okay, we did that. Find the volume of the solid. You know what? I'm going to add a part. I don't know. I'm going to call it part A2 because I want you to know how to do this. Find the area. We want to find the area of that region. Okay? Because that's a good thing to always do beforehand. This is mostly a volume question, but let's talk about area 2 of R. Okay? So that has to do with subtracting the two functions together. And the way you want to think about this is the pink function is on top of the purple function. So which way does it make sense to subtract it? You're going to subtract the top function by the bottom function because the function values of the top are more positive than the lower ones. We want to get a positive area. So what that's going to be is the integral of 6 minus x minus square root of x. And some of this will come into play later. Hold on a second. I'll make sure this doesn't. Just trying to end my meeting. 6 minus, okay, dx. Then what happens? Well, before we actually take this integral, remember that this is going from 0 to 4. Because 4 is that intersection point we care about. So what are we going to get? Okay, opposite of the power rule, we're going to get 6x minus x squared over 2, and you got to divide by that 2 that the power is now, minus x to the 3 halves. You got to divide by that 3 halves, or in other words, say 2 thirds. If you want to divide by 3 halves, go for it. Either way will work. Okay. Whatever way makes more sense to you. And we go from 0 to 4. Fortunately, hopefully you all can kind of see that if we plug 0 into that thing, it's all going to be 0. So you can kind of ignore that little guy. For the first one, though, the 4, let's do 6 times 4 minus 4 squared over 2 minus 2 times 4 to the 3 halves over 3. Okay. That gives you 24 minus, we'll write it. We won't be lazy. 16 over 2 is 8 minus, okay, this last one. So 4 to the 3 halves. What does that mean? That means to take the square root of 4 and then cube it. Why? Because the 1/2 power, a way you can write that, color change, hold on, so we don't get confused. 4 to the 3 halves is just going to equal basically the square root of 4, because 1 over 2 means square root of. You can pull out a 1 up over 2 here. Okay, but if we do that, then we still have that 3 that's on top. It's the square root of 4 to the 3rd power. Again, we're assuming the worst, that we're not allowed to use a calculator here. So it's going to be square root of 4 to the 3rd power, and that's going to give you 8. Okay, 24 minus 8 is 16, minus 8 is 8. And that is your overall area of this shape, okay, of the region. Next, find the volume of the solid formed when region R is rotated about the x-axis. Use the washer method integrating with respect to x. Okay, so what happens now is this region, all right, we're going to mess up our beautiful picture here, is going to go around. Right, we're going to take this whole thing. It's going to be basically wrap around the x-axis. Okay, so the proper way to approach this is to look at the pink line because that one's on top. And again, then we're going to subtract by the purple function that's on the bottom. And you want to find the area, or sorry, the volume of both. So I'm going to erase that just so we can doodle on it more later. And what is that going to look like? Well, let's take one function at a time. If you remember, okay, using the washer method, it's like you're treating it like the area of a circle, basically. It's a rotation. So it's pi r squared. Right? When you rotate something like that, that makes sense because it's like you're taking each little line here and saying, let's rotate it around. And we want to find the overall volume of that. Which again, is kind of like a collection of areas of circles throughout this function. So anyways, we get pi. You can write it on the outside or the inside. It doesn't matter. It's a constant. R, what's our radius? 6 minus x squared dx. Okay, and then what we can do is we can expand that. We can say pi integral from x squared as before minus 12x plus 36 dx. Okay, and where is this from? This is from, again, 0 to 4. That's where the intersection point comes into play. Okay, so what do we get? We get x cubed over 3 minus, this is going to divide by 2, so it's 6x plus 36. Oh, sorry, that was the x squared. 36x. And the constant doesn't come in. Why? Because what type of integral is this? This is a definite integral, meaning it has bounds. So, the constant would kind of wash away. Haha, little washer pun. Okay, so we're going to go from 0 to 4. And what do we get? 4 to the third power is going to give us 64 thirds minus 6 times 4 squared is going to give us 6 times 16, which is 96, plus 36 times 4 is 144. What does that equal? And yeah, we still have to do another integral. We're just finding this volume first. I don't think we'll solve the last one. I just want to. The important thing with these is that you know how to set them up. Okay, especially if you feel confident in your integral skills. This is really where visual math meets, the actual integration that you've been doing. But can you convert what you're seeing visually to the integral? Okay. So what are we going to get? That's 48. 64 thirds plus 48. 64 thirds is 21 and a third. Okay. And then we're going to subtract. Yeah, that's right. Then we're going to subtract the other one, which is the so pi. Oh, that works out nicely. Still in part B, everybody. Pi integral of radical x. Oh, but wait a second. It's squared dx equals, okay, radical x squared. Guess what we get? We get x squared. And we get regular x. Sorry, I was thinking about something else. We forgot our pi here. Boop. Sorry, jumping all over the place. So it's 69 and a third pi, right? Down here, when you square the square root of x, you just get x. So it's pi integral of x dx, which ends up giving you, still from 0 to 4, we get pi times x squared over 2 from 4, I should say 0 to 4. And then we plug it in, and we're going to get 16 over 2, which is 8 times pi. That's your answer. 69 and a third pi minus 8 pi, which, by the way, equals 61 and a third pi. And if it were presented as an improper fraction, that would be 184 thirds pi. Okay. Hopefully that makes sense. This one is with respect to x, right? We have a function. We've got y equals a function that's in terms of x. And the reason for that is we're rotating around the x-axis because it's rotating around a horizontal axis, a horizontal line. Then that's basically what we're using. Okay, so part C. Okay, now you want to start to shift everything to in terms of y. Okay, so instead of being in terms of x, let's shift our equations over. Okay, so this one is on the tougher side for sure, especially because the line that we're rotating around is x equals 5. The question says, find the volume of the solid formed when region R is rotated around the vertical line x equals 5, which is, again, out there. Use the washer method, integrating with respect to y. Again, the way you can picture these is you've got this giant solid that's formed by rotating this green thing all the way around that dotted line. Okay, and then on the inside, look more like that. And a good way to approach this is, okay, let's consider the outer region with its own outer radius, and then we want to subtract out the inner radius. So the outer radius is actually kind of easy, okay? It's hard to think about, but it's actually easy. Basically, if we put one of those back, the big radius right there, it's the same for all of these points, okay? And where does that go from? It goes from y equals 0 to y equals 6. We're going to get basically a solid cylinder. And there's two ways to think about a giant solid cylinder is, without a changing radius. What is the formula for the volume of a cylinder? Some of you might remember that outer, so I'm going to say V outer, equals pi r squared h. And where does that look like on an integral? That's actually the same as saying pi r squared. You can say integral r squared from 0 to 6 d, and then whatever variable you want. You can think about it as height, right? 0 to 6 would represent the height of the cylinder. That's really what we're doing. But in this case, we're just going to have a solid cylinder from 0 to 6. So what that looks like is pi r from the y-axis to the line x equals 5. Think about how far that outside radius would be. If it goes from the y-axis to x equals 5. 5. Hopefully you can picture that, right? It's going to be a cylinder with radius 5. It goes all the way around. Okay, so we say 5 squared. Height from 0 to 6, that's just going to be 6. What do we get? Well, that's 25 times 6 is 150, or 150 pi. That's not the answer. Okay, let me show you the integral way to do this. You're going to get pi integral from 0 to 6, where your radius is 5, again, because that's the distance from the outside to there, dh, and hey, look, oh wait, no, 5 squared, radius squared, don't forget that. 5 squared is 25. Integrate 25, you get 25h. Hey, look at that, we have the exact same thing. Pi times 25h from 6 to 0, which, like we just talked about, is going to end up giving you 150 pi. Again, that's not the final answer. Okay, so it's going to be that integral, okay, any of these things minus, what's the inside going to look like? Okay, this is where it gets weird. And I want you to try to picture what's happening here. We've got that giant cylinder around this whole thing. Again, it's hard for me to draw this without just making things super confusing. That whole big cylinder minus, I guess we'll draw it in orange. Okay, picture this line from here to there. How are we going to get the horizontal distance from this red line to this curve, y equals 6 minus x? We're going to subtract it, okay? Because what is that x value? It's going to be 5 minus, well, what's the x value at that point? We didn't do that yet. Okay, so back up a second. One thing we're going to have to do here, before we talk about that, and yes, we still need that orange radius, we're going to have to convert this into terms of x. And to do that, we're going to add x. You're going to get 6 equals y plus x. And then we're going to subtract y, and now we've got it solved for x. That's actually going to be the x equals version of that top curve. Okay? Then on the bottom, what do we do? Well, we can square x, and then you're going to get x by itself. So you'll have x equals y squared. Okay? And technically, because it's only the purple curve, okay, we're going to care about, we only care about the positive values there, first quadrant, okay? But that won't really come into play because of the way we integrate this. So the first one we're going to look at is here. x equals 6 minus y. And we want to figure out basically the distance from that red dashed line, which is x equals 5, remember, to 6 minus y. How do we find that distance? How do we find this orange line here? We're going to subtract x equals 5 minus 6 minus y. So the curve is going to be 5 minus 6 minus y in parentheses. Distribute that negative, and it becomes 5 minus 6 plus y, which ends up being y minus 1. So what we're actually integrating is x equals y minus 1. I want you to remember that what we are so we're using that as the radius, the inner radius for this curve. Whatever the x value is, okay, whatever the y value is, subtract 1 to that, and you get that inner radius, is what that's saying. And if you look at this, if we look at a y value of 6, we subtract 1, we now have 5. That's right here. Inner radius of 5. That makes sense. That goes from the y-axis to x equals 5. That's 5. Which actually means you're subtracting out the whole thing at that y value. As you go down, let's say we go down to y equals 5. 5 minus 1 is 4. That would be a radius of 4. Which makes sense because we're getting closer. We subtract out an inner radius of 4. We keep going, but we don't go all the way down to 0. Think about what the bounds would be here. The bounds are going to be x equals 2. Nope, x equals 4 or y equals 2. Because at this intersection point, we switch curves. Okay, so we would say 150 pi. And by the way, some of you might be thinking, wait a second, that first curve we did, wouldn't we have to split that up too? You could split it into 2 to 6 and 0 to 2. Right? Those are the two versions of the y limits here. You've got from 2 to 6, which is the top part. That's basically up until here. And then you've got from 0 to 2. The thing is, if we split up that outer radius, it doesn't really matter because the curve on the outside, that y-axis to the x equals 5 line, is always 5. You can literally just use the cylinder formula to find that. What we need to find now is the integral from 2 to 6 of this into the cylinder, the rotational formula. Call it cylinder, but it's not exactly a cylinder. It's getting us toward a washer, right? Which is really what this type of thing is. So we would take pi from the integral 2 to 6 of y minus 1 squared dy. Again, because this is a line around the line x equals 5, this is a tricky question. Okay, don't get me wrong. Part C is very difficult. It's on the harder side. If you feel confident about this, you're on track for a 5 for sure. If you're struggling through part C, you might be in the 3-4 range. But it's a hard part C for sure. But what we're doing is, again, you're taking x equals 5 and you're subtracting that by the function in terms of y. Okay. This thing just keeps trying to turn off. All right, so that's the first integral. And really, I'm just going to set this up for you. Okay, so I just want you to understand it. So it ends up being 150 pi. Erase over this in black. I just want you to understand the setup. Minus pi from 2 to 6. This is the top part of the curve. Y minus 1 squared. And again, that y minus 1 represents the inside radius of the washer that you're subtracting out. It's like if you were to take a quick little sketch so you can try to understand this visually. If you filled this all in with green, right? And then you say, but wait a second, I have this funky shape on the inside that goes like this. And it might be very strange. We want to subtract all that out. That's basically what we're doing here. Whereas the black and green part represents the y-axis to the curve, or to x equals 0. Try that again. y-axis to x equals 5 rotated around, and the red part on the inside represents the funny function business going on here. Okay. So now we have the other one that we found in terms of x equals y squared. And what we have to do for that one is the same thing. The radius we want to subtract out goes from x equals 5 to the curve. So that means we're going to do x equals 5 minus y squared. That's it. Again, that means the radius we're subtracting out, the inner radius at 0, is 5. We subtract out the whole thing, which makes sense because there's nothing right here that we would substantiate when we rotate it around. But as we get up to the intersection point where x equals 4, y equals 2, 5 minus 2 squared is going to give you 1, which just means we're subtracting out just a little bit from there to there. Okay, so the last part is minus pi. The bounds are going to be 0 to 2, right, from the x-axis to y equals 2. And the radius is going to be, what did we just write here? 5 minus y squared. It's going to be squared dy. And that, again, 150 pi we actually solved, right? Then you're going to subtract out those other two integrals that, again, what they represent is basically, I was going to say white space, but all the orange space here. Imagine all this orange space that I'm coloring in. Rotate it around like this. Get this rotation right. Rotate it around. Subtract it away from the pink cylinder part here. We subtract out the orange space that's here. And we got that by calculating the distance from x equals 5 to those the red and purple curves, okay, depending on where the y value was. Okay, so again, that part C is on the more difficult side. I would focus a lot of your energy on totally understanding A and B. And again, if for those shooting for a 5, study part C. It's some of this stuff. It's not going to come naturally. It's just asked in a difficult way, which makes it harder to get to the end. So hopefully, you at least followed along for parts A and B and struggled through it. If you made it this far, I would encourage you with the exam coming up or whenever you're watching this, I am helping AP Calculus students get 5s on the exam, 4 if that's your goal. So just follow the link down below. Set up a free time with me. And if nothing else, I can give you some pointers in the right direction to, do well. I don't want you to struggle. Turn this off. I don't want you to struggle with this exam. I firmly believe that everybody taking AP Calc, you got this far, you're able to do well. You're able to get that 4 or 5. So the worst thing that can happen is I'll give you some suggestions. We'll decide that I can't help you further, and that'll be it. And, yeah. Again, it's free. It's a free session. I work with kids and teens like you a lot. I like this stuff. Hopefully that comes across in the way I teach it. I loved math my whole life to the point where it became my career. I started as an actuary, and then eventually it led into teaching, and now into this. And I love it. I love every day of it. And if I can help you too, I would love to. So again, follow the link below. No pressure, no commitment, but I would love to be able to help. Thank you all, and I will see you in the next one.